today?
Say this again?
Do we have another test that you're handing out today?
Yeah, I've got 2 that I'm going to hand out today. Y'all asked for both of them, didn't you?
No, we just asked for 1.
What's that? Okay, just a second. Let me pause this then. Okay.
Nobody asked for 2. He said he was giving us 2.
Let me pause here. Whoop, hit the wrong button. Okay, wait a minute. From current slide and pause. If you need to review this again, you can hear it again. Okay. First, let me say this. Has everyone done student course evaluations?
Yes.
Okay. Several have. The rest of you, please do. Okay. You can wait till the very bitter end if you want to, but just don't forget about it. Okay. Because I know that, I think I've said this before, when I was in college, that last final exam, when it was over, the brain was turned off and I was heading home mentally, whether I was heading home or not, and I would never have recommended waiting till the very end. But if you can remember, go for it. Okay, so that's first. Second, let me give you an idea of my schedule. Let me first, this doesn't look like, yeah, I guess that is the last slide we did. Okay. All right. Here's what next week is going to look like. Well, rest of this weekend next week. Okay, today we have class, of course. Tomorrow I'm on the Bessemer campus all day. Friday I'm here on the Birmingham West campus, in Dr. Pruitt's office, there. But we do have a meeting late morning, I think. I don't remember the time of it, 10 o'clock or something like that. 10:30 maybe, something like that, we have a meeting. Now, I heard rumor there may be 2 meetings, but we'll deal with that when we get there. But anyway, I'll be there early in the morning, so if you need to see me, 7:45 to 9, they hardly ever start meetings before 9, so I'll be there until then. Okay, Monday. Monday starts finals week for the full-term classes, but it's the last day of class. Monday and Tuesday are the last day of class for second mini-term classes. That's us, here. So, Monday from 7:45 in the morning until 2 in the afternoon, I'll be in my office or around my office, somewhere around there, on the Bessemer campus, room Ace 265, because I don't have any classes in the morning, but I do have a final in the afternoon from 2 to 3:50. But this class starts at 4. But I've already arranged, that's one of the delays that I had. I tried to see the instructor who has a class right next to mine, right after my class, but he had stepped out somewhere. So I was proceeding to leave to come, get ready to come. And I was stopped by another instructor in the hall to ask me something about a meeting I have to go to next week. So we were talking in the hall when this instructor came by, and I asked him, and he's going to cover, when it gets to be 3:15, then I'm going to either ask him to come into my classroom to proctor the test, or I'm going to send my students to his classroom to finish their test. So I should be here, knock on wood, by 4 o'clock on Monday. We'll have our last class Monday. Tuesday, 8 o'clock, I've got a final on the Bessemer campus, 8 to 10, approximately 9:50 technically. And then I'm free from 10 o'clock until 1:15. Then I have my second mini-term class that meets from 1:15 until whenever they finish. Because we don't have much left to do in that class, and because I'm going to be out of town on Thursday, we have to finish the material, do the lab, they have a lab, and then have their last test and their final exam. So I've got those 4 things to do we're going to finish the chapter hopefully tomorrow, and maybe even do the lab, but then they'll have their last test and final on Tuesday. Okay, Wednesday, I'm still on the Bessemer campus, and I'll be there from 7:45 in the morning until 6 o'clock. I see no reason to come here unless some of you want to turn in your test on Wednesday. Would it be more convenient for me to come here and collect them? Up to you. What's that?
I can take it over there.
Okay. Are y'all just as convenient to take it to Bessemer, or is this more convenient here? Because I'm used to coming here. I can come here. That's on my locator card. What you think?
Can we fax them to you?
You can. I don't have my fax number with me, and I don't have a fax number in my office. You'll have to send it to the faculty staff secretary fax number, which I don't have with me. I can get it for you if you need that. You can email it to me if you want to scan it and email it. Okay, now let me ask you to do this. Don't take pictures of it and email that to me, because JPEG files my old computer won't read. So I can get them. Ultimately, I have to get someone with a newer computer to print them off for me, and then I can grade them. But if you do a PDF file, I can pick up those. Okay? But JPEGs and the other, there's some other picture files that my computer's just too old for that. It's a 16-bit rather than a 32-bit, so it just won't do anything with those. All right. So that's through Wednesday. So no one needs me to come here Wednesday afternoon. I'll be glad to do it because I'm used to doing it, and it's on my way home, so it's no problem to do it. But y'all don't need me to? Okay. Well, then either bring it to the Bessemer campus, email it to me, or if you finish both of them by Monday, you can turn it in Monday. Yeah, that's up to you. We won't have covered all the material before Monday class, but if you can do it, that's fine. Okay, then, if this is more convenient for you, it's fine too. Thursday morning, I'm not going to Bessemer. This is a finals week, not tomorrow. I'm going to come to Birmingham West Campus, because that's when we load up in a van and head to Tallahassee. But they're not going to leave until around 10-ish or so, and so I will be on the Birmingham West Campus, Dr. Pruitt's office, in there from about 7:45 in the morning until whenever we leave, which I think is around 10. But knowing them, it's probably going to be later than that. No one ever seems to. Yeah, driving to Tallahassee, spending the night, and driving back late on Friday night.
No.
What a pain in the neck, or some other body part. Okay, so, yeah, and it's a worthless thing, as far as I know. They've already been there. They've seen the building. They modeled this new building after it. Why are we going now? It's to look at their labs. Well, guess what? I've seen labs before. There's just really, maybe we'll learn something there, but I think it's a huge waste of time. Okay, it's like Betty White said when she won an Oscar for whatever that role that she was, that it was about Facebook, and she had never been on Facebook, and she said, they said, what do you think of Facebook now? She said, well, I'd never even heard of it, never been on it until the movie. But now, I feel like it's an enormous waste of time. So yeah.
How long is it going to take you out of here?
How long to what?
How long is this trip going to take you out to get there?
They said 5.5 hours.
Are you grading papers on the road?
I doubt if I'll be on the road, but that evening we have some dead time in the room. I'll be grading papers then.
Oh
Yeah.
my God.
Okay? And then the next morning, I'll be waiting around for them to come by. Because you see, another evidence of great planning, guess what? It's Florida State's graduation weekend. And that's in Tallahassee. And therefore, traffic is awful. And therefore, getting rooms is awful. As far as I know, we're in 3 different hotels because they couldn't get a block big enough in any one hotel. So that means in the morning, whoever has the van's got to drive around to 3 different hotels to pick us up to get us to the meeting. They better be. But actually, we have to put the rooms on our credit card. We have to pay for them, and then the school's supposed to reimburse us. So, okay. So, it's no way to do business in my mind. Okay. All right. So anyway, Thursday and Friday, I'm off campus after 10 o'clock Thursday morning. I'll be back late Friday. So anything, if you turn it in Thursday or Friday, before 10, catch me on the Birmingham West Campus. Otherwise, take it to the Bessemer campus, slide it under my door. I'll pick it up Monday morning, and I'll grade them then. Okay? So if you're running late and it's Thursday and it's inconvenient for you to come here, but it's more convenient to go to Bessemer, or if it's after 10 o'clock, go to Bessemer and slide it under my door, slide them under my door, whatever, and then I'll pick them up Monday morning and grade them then and get the grades in. Grades are due either Monday afternoon or Monday at noon or Tuesday at noon. I don't remember which day, but yeah, so I've got a lot of grading to do before then. So, all right, any questions? I'll return all the papers that I've gotten graded, that you've turned in, I've got graded on Monday. So, that. Any questions? I know that took way longer than it probably should have. All right. Now, where we left off last time was on 17.9 compound circuits. I was thinking we didn't need to cover this, but it seems like something in the course description indicated we probably did, because I had marked 17.9 as the last section in 17. So let's go for it. Now, what is a compound circuit? Well, we've done circuits that are, this one is in fact, this is not a compound circuit. Let me turn here. Here's one. Here's a compound circuit. All right. You have this resistor in series with these two, but these two are in parallel with each other. That's what they mean by a compound circuit. So how do you deal with one like this? We have rules for series circuits. Well, I meant to ask this first. Sorry, time out. Any questions for anything we've covered so far? No? Okay. I always want to ask that. Last time we had quite a few. So want to make sure I wasn't leaving someone hanging. Okay? We've had what you do if all the resistors are in series, you add the resistance. If all of them are in parallel, you do 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3, whatever. So you come up with equivalent resistance. Well, what do you do if one's in series with the other two in parallel? What do you do there? Well, you do an equivalent circuit. You pretend number one's not there. You do this equivalent circuit and make that R4, okay? And you do 1 over R2 plus 1 over R3 is equal to 1 over R4. And then calculate and see what R4 would be. Then those are in series with R1. You add those two together and that gives you R5. Does that make sense? You know how to change this to an equivalent resistor. That gives you R4. And then how to combat those two in series. That gives you R5. And that's your equivalent resistance. Make sense? Okay, now some of these can be sort of complicated. I doubt if we'll do too many that are that complicated. But in this figure right here, no. All right, sorry. Here is the one that we're looking at. I thought this was the top of the page, but it's not. Okay, here is the figure. We're looking for circuit B. Well, actually, the figure doesn't match the example. Circuit B in figure 1751. That's, in my books, figure 1751. Is that in yours too? Okay. And that's the one that's on the slide here. It's the one in the book. Okay. But it says there is equivalent to circuit A, where R4 is R1 plus R2. Okay, got it. This is a, oh, okay, no. All right, sorry. Got it. I'm sorry. I was misreading this. Okay. They don't show the power supply anywhere here. They're just showing the resistors. Okay, these two, sorry about this. Okay. This is right. These two are in series with each other, and that equivalent resistor is in parallel with that one. So what we do here is R1, two resistors in series, you just add the resistances. R1 plus R2 is equal to what they're calling R4. That's your equivalent resistance over here. Now these two resistors are in parallel, and what you do here is 1 over R4 plus 1 over R3, those two in parallel, is equal to 1 over R5, the equivalent resistor there. Okay? So how do you get R5? Then you do the mathematics to get that. They didn't give you any numbers, they just basically had the circuit diagrams. Okay? Sorry about that. Any question on that? Do you see how that works? Okay. If you remember, two resistors in series, just add the resistances. That's why R4 here is just the sum of those two. There's not really a new resistor there. It's the equivalent resistor to those two added together. Okay? Now this is in parallel with this one. Parallel rule is 1 over R4 plus 1 over R3 is equal to the equivalent resistor, which they're calling R5, 1 over R5. You do the math that flips that back over, and then you know what the equivalent resistor is. Okay? So that's example 1 on 17.9. Okay. Any questions on it? Okay. And here is example 2. Okay? And again, they're not giving you any numbers. I was looking for numbers, but they're just giving you diagrams. On this one, you need to calculate the parallel resistor first and come up with something equivalent. That's going to be R4. And because those are parallel, what would be your representation there? 1 over R2 plus 1 over R3 will then yield this, 1 over R4. Okay? So you have to do the math, do the fractions, flip them over, and find out what R4 is. Then once you get R4, the equivalent resistance of the whole thing will be R1 plus R4. Whatever that calculated to be, that gives you R5. And that's how you do a compound circuit that has both series and parallel resistors in it, depending on which ones you have to consolidate first. Okay. The next one actually does give you some numbers. Does anyone need this any longer? Got it? Okay. But they don't do the next one. Okay. The next one is actually find the total circuit in the circuit shown in figure 1753. Now, I don't see a 1753 on here, so I'm going back to find something close to it. This is close to it. Not quite the same, but close to it. Okay? What is different here, and I don't know why they use R3 and R4, but, okay, we'll pretend, you want to pretend, okay, yeah, it's pen, okay, that time it took. Okay, we'll just eliminate R2 altogether there, and what we'll do is put an R4 up here, okay? Why they chose 3 and 4, I don't know. So here your E is 115 volts. Okay, now just for your cultural information, Most of the times you don't have batteries at 115 volts, okay? That is really, really big voltage for a battery. That would be a series of batteries. This is probably AC, but it doesn't really matter here. We're doing the equation here. That's not the symbol for AC, but normally AC is like 120, but the time you get to the wall socket is easily 115. So, but that doesn't really matter here, okay? So here's your problem. R3 they give you as 19.0 ohms. Okay. Find the total current shown in this circuit. Oh. No, they put the circuits in here backwards. Okay, wait. Let me find out. What's that? All right. All right. Sorry. I was trying to do what they were doing, but I found out they drew the things backwards. Here's where we start. Okay? Here's 1753 on the right. Forget what's on the left. 1753 is on the right. Okay? And here it is our E here. Long bar, short bar. Okay? And it goes around here and does here. All right, there's the circuit we've got. Here the E is 115 volts. All right, now we got it. That's why they left out R1 and R2. R1 is 10 ohms, 10.0 ohms. R2 here is 32.0 ohms. And R3 is 19 ohms. Okay, that's what we got. There's our circuit. Okay? Now, just like what we did before, the first thing we've got to do is come up with an equivalent resistor to these two in series. And what would that be? Pretty simple. What would our R4 be? That is the equivalent resistor to R1 and R2. What would it be? When you have two resistors in series, what do you do to the resistances? Add them. So R4 would be 42.0 ohms. And you see why we use the Greek letter omega. What if that was an O? It would look like 42.00. You know, that's not right. Okay. All right. Now we have these two in parallel, and the R3 hasn't changed any. It's still 19.0 ohms. Okay. So how do we get R5, the equivalent resistor? How do we do that? These are parallel. How do you combine parallel resistors? 1 over R4 plus 1 over R3 is equal to 1 over R5. Okay? Now, we can do it literally, or we could do it with the numbers. Which would you rather do? With the letters or with the numbers? Say again? Numbers. Okay, we'll go on and plug in. This will be 1 over 42. I'm going to drop the point zeros because they just make it messier. We'll put them back in at the end. Over plus 1 over 19 is equal to 1 over R5. And that's what we're looking for, right? And by the way, the question is find the total current in the circuit. What we're looking for is the I, which is here, okay? Not I that goes to any leg, the one that leaves the battery and comes back to the battery. Okay, so this will be, okay, again, you want the kind of the straightforward way to do this or do it the longer way? Straightforward. Okay. I hope you realize this. And do y'all love fractions? Really? Oh, wow. That's an unusual class. Most of the time people just love, no, they really don't. What I'm going to do is multiply by the least common denominator of all the denominators. Because this is an equation. You can multiply both sides by anything you want to. Are there any common factors between 19 and 42? I think not. Okay? So therefore we're going to multiply this and this and this by 19 times 42 are 5. Multiply this by 19 times 42 are 5. And multiply this by 19 times 42 are 5. Okay? Over here, the 42s cancel out, and you have 19 are 5, plus, here the 19s cancel out, and you have 42 are 5. And over here, you have the R5s canceling out, and whatever is 19 times 42. Someone punch that in for me quickly. See how violent we are in the South? We say punch it in, press it in, or whatever. Okay? What's 19 times 42? 398? 798. That sounds better. 798. Okay? Now, we're going to add those two together, and that gives us 61. R5 is equal to 798. Okay? Divide both sides by 61. And what does that give you? Say again?
I was saying they're going to get R5.
That'll give you R5. Yeah, exactly. Say it one more time. Okay, 13.1. Okay. Well, you might want to keep the 08. Hang on. I'll keep it because you gave it to me. I'll keep it. I'm not going to throw away your gift. Okay, that's going to be ohms. Okay. Okay. All right. 13.08 ohms. Okay. Now, time out and ask yourself, does this make sense? Remember, in parallel resistors, the effective resistance has to be less than the least of the two resistors, or 3 or 4, or how many you got in parallel. Here we had 2, 42 and 19, 13.08 certainly is less. That makes me feel warm and fuzzy. It doesn't tell me it's right, but it does make me feel good that it's the right magnitude. Okay? Now, what we do with that, we know the voltage is 15 volts. The effective resistance is 13.08 ohms. So how do we get the current? How do we get the current? I equals E over R. Great. Okay? And that would be 115 volts divided by 13.08 amps. And what would that give you? Something less than 10 for sure. 9 something? A little louder? 8.79. 8.79 what units? Amps. Very good. Let's see how the book did. They got 13.1, which I would have rounded that had we rounded. And then they carry on they got 8.78. And here's why. They rounded too soon. Yeah, you should keep all the units in there until your final answer, then round that to 3 decimal places. But if you're within 1/100th of an ampere, you're close enough, okay? So I'll let them get by with it. Okay, they did show you at the top of the page one other way to do your calculations on your calculators. 19, I think the way we did was more straightforward. But 19x to the minus 1, 19, and press the key x to the minus 1. It's a reciprocal key, plus 42 x to the minus 1, and that gives you an answer. Do x to the minus 1 again, reciprocate again, and that gives you 13.08. Is that a 7 or 1? No, 1. 96721. Okay? I would leave all those on the screen, divide that into my 115 and see what you get. Anyway, that's your effective resistor. Okay. Now, example 4, we don't have anything that looks like that. So what I'm going to do is erase what we've got here. If I can find my key, there it is. Okay. Did anyone need that left up there a little longer? I went on and left the screen. Okay. Let's do example 4. Okay. Okay. Find the equivalent resistance in figure 17.54. Okay, so here you have your battery, and the E is 120 volts. And by the way, that's not a battery, okay? With that much voltage, you're AC, okay? But it's okay. And then we got 3 resistors in parallel. 1, 2, and 3. Okay? And that runs around until you catch and get 2 resistors in parallel. I can't draw these very well, obviously, okay? And R1 up here is 7.00 ohms. That's a 7. R2 is 35.0 ohms. R3 is 25.0 ohms. Okay. R4 down here is 20.0 ohms. And R5 is 62.0 ohms. Okay, I think I've copied it right. Now, what would be your approach to a problem like this? And what we're asked to find the equivalent resistance in the circuit. They didn't ask for the current. So who cares what the voltage is? You won't need it in this problem. All they're asking for is equivalent resistance. Okay? But don't throw it away because example 5 will ask for the current. Okay? So just don't erase it too soon. All right? What's the equivalent resistance? What would you do first? Say again? I can't hear you. How? And which ones? Okay, how do you do that? 1 over R1 plus 1 over R2 plus 1 over R3 is going to be 1 over, and I think they'll probably call this R6. That'll be the equivalent R6, the equivalent resistance of these 3. When you do these together, you're going to get an R6. Okay? And that's what that will be. Okay? Now, this might be where paying attention to their little rules on the calculator will come in handy. Remember how to do that? Do you have a calculator with a reciprocal key? R to the minus 1 or 1 over x or something like that, x to the minus 1, something like that. You do. Okay? What you would do, would put 7, hit the reciprocal key, plus 35, hit the reciprocal key, plus 25, hit the reciprocal key, equal, and you get a number there, right? Then hit the reciprocal key again, and another equal, and your R6 would equal what? 4.72, and we'll keep the 9 for now. No, we really don't need it. Let's make it 73 ohms. Okay? Does that look like it makes sense? Yes, these are parallel resistors. The effective resistance has to be less than the least of those. And the least of those was 7. So 4.73 at least makes sense. Okay? Next. What would you do with these two down here? What would you do with those two down there?
You gotta find R7, right?
Yeah, they're calling R7, right. How do you find it? 1 over R4 plus 1 over R5 is equal to 1 over R7. So the equivalent between these two will be R7. And how do we get that? That's 1 over 20 plus 1 over, is it 62? Okay. Is equal to 1 over R7. Okay, and again, what you can do, using their little algorithm, is 20 reciprocal key plus 62 reciprocal key is equal to, whatever that comes out to be, hit the reciprocal key again, and what do you get R7 to be? Say again? 16 or 15? 15? Okay, 15.41? 0.1. Okay? Ohms. Okay. Now, what do you do with the R6 and R7? What's that equivalent to? Okay, and how? R6 and R7 are, how are they related? They're in series with each other. See, the same current that goes through R6 goes through R7. They're not parallel. Those are in series. So what do we do to get that effective resistance? R8 would then be just add them together. That would be 19.4, wouldn't it? 19.4 ohms. Okay, do you see how that happens? 19.8. Well, y'all must have told me something wrong. Oh. No, I'm sorry. I added wrong. It's 19.43. Wait a minute. 19 point. Oh, it was 7.3. I'm sorry. Yeah, sorry about that. Let me erase. My bad. Okay. I can't read my writing is what it is. Okay. Take your time. Enter these on a calculator. 4.73 plus 15.1. Is that right? That'd be 19.8. And if they say 8.3, that's fine. But that really makes no sense. You can't have more than 3 significant digits. So it's really 19.8 ohms. Okay? Make sense? Now, the example 5 part says, find the total current in that example. Now we use our E. And how do we find current? Total current using that. Somebody came up with it before. I is equal to E over R, and that's the effective resistance. In this case, it'll be R8. So it'll be 120 volts divided by 19.8 ohms. And that's going to be something just more than 6, right? 6 point what? 6 point what? 0.6. Is that what you said? And that would be what units? Amps. And let's see. Oh, look at that. They got it right, didn't they? Good for them. All right. Now, a table you've seen before, but now put together. It was 2 tables, now it's 1. Okay? Characteristics of series and parallel circuits. If I can stand up. My knee is sore. When I sit too long, it really hurts to move. Once I move, it feels much better. Okay, in a series circuit, okay, your resistors, you add them up. If each of those in series with each other, you add them up. But the total current is the current through each resistor, because the current moves through this one, through that one, through that one. You don't lose current. You can't destroy current. You can't destroy charge. You've got the same charge, so the current's the same through all those. The resistance is add, and therefore your total voltage is the voltage drop across each resistor. Because the current's the same, each resistance is what it is, you can calculate the voltage drop across each resistor, and those will add up. That's when you've got a series circuit. When you've got a parallel circuit, then every leg of the parallel circuit has to take the total current and send some here and some there and some there, so the currents add up. Like the resistances there, the currents add here. The resistances add by the reciprocals. 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. You use your inverse keys on that. But the voltages, is a pure parallel circuit, that's the same across every resistor, because those 2 pins there. Now, your voltage usually is fixed too, meaning the more resistors you add, the more current you're adding, okay? And the effective resistance is going down, down, down. Always less than the least of those resistors. Okay. That's all we were supposed to cover in chapter 17. Now, I tried to make it that's all that you're testing there. They show you some electric instruments, and I was just wondering if any of these came close to being what you'll be needing, and I doubt it. I meant to say this. Problem set you might want to do, any of the, I think it's odd problems, 1 through 5, using figure 17.55. Any of the odd 7 through 11, using figure 17.56. Then using figure 17.57, any of the odd 13 through 19, and using 17.58, using any of the odds 21 to 25. Okay. Now the electrical instruments, my looking at this, basically are showing multimeters, which are either ammeters or voltmeters. Possibly ohm meter, but I didn't even see any of those talked about. Okay. Then it looks at voltage sources. Certainly you have batteries. Now, the one thing we didn't do, but I don't think you need this, is when you put batteries in series, but I think we did this early on, didn't we? If you put batteries in series, you're adding the voltages. Put them in parallel, you take the voltage of the greatest of those in parallel. Okay? When you're adding voltages, you're increasing currents. Okay? When you put them in series, your current is limited to whatever the greatest one of those is. So that's what 1712 is showing. I'm not sure you ever have to do this. However, if you're jumping off your battery, you might have to do that. You do these in parallel. You put plus to plus, minus to minus. Don't do it the other way. You'll drain your good battery. Okay? Put plus to plus. You may also drain your battery the other way, but that's how you recharge. Electric power, I don't think you need that, if my understanding of what y'all will be doing is fun thing, good concept. Wish we had time for it, we don't. They talk about Tesla high-performance electric automobile. If you're interested in that, it's worth a look. But otherwise, don't sweat it. The formulas here, most of these formulas we did go over. We didn't do the ones on power, but we did most of them up to 17.3 through 17.12. Review questions, you can certainly look at those if you'd like, and review problems, but just don't get bogged down on stuff we didn't do. Okay. There's an applied concepts here. I don't know if you find any of those useful, but you can deal with them. Let's move on then to, let's see, what I'll do is, wrong key. I can't hit the right button here. Okay. All right, let's move on to chapter 18. And we don't have many sections here. The ones I put down were 18.1, 18.2, and 18.7. I don't think you need generators and motors. I don't think you do, but if you do, we'll deal with it. Okay, so let's do 18.1, 2, and 7. Okay, magnetism from the current slide. All right. Just generally, we've known, meaning mankind has known, about magnetism long before we knew and understood anything about electricity. And for many years, I would say decades, maybe centuries, they were thought to be completely separate. Magnetism, this is magnetic, this is electric, okay? But people began to notice there were relations between them, okay? Let's start with just what we know. Here is a fairly reasonable figure. What this is are two magnets, the north pole of one magnet, the south pole of another magnet. And by the way, here's some differences that we have. Electric charges. You can have an isolated positive charge out here somewhere. No problem. You can have an isolated negative charge out here. No problem. With magnets, we have what we call poles. You cannot have an isolated north pole. Everywhere you have a north pole, you got a south pole. Everywhere you got a south pole, you got a north pole. You cannot isolate. Now, if you'll notice here, here's the north pole of one magnet, south pole of another magnet. And what they've done, they've put it on a piece of paper and sprinkled iron filings. And you can see the iron filings line themselves up according to the magnetic field lines. Remember we talked about electric field lines? Magnetism has field lines also. You can't see them. You can see the iron filings as they line up that way. Now let me get you to imagine that we extended this. Well, let's just imagine it this way. Forget this and forget this. And let's just imagine that's one bar magnet, south pole there, north pole there. Okay, forget the iron filings here. And what you would see that lots of iron filings line up here and go in all directions, here in all directions, and a few of them may loop over and do like this. You can almost see some of them trying to do that here. Okay? The point being, your magnetic field lines are concentrated around the poles. None in the middle. You don't see any iron filings here. This is too short here, but you would. If you really had a magnet there, you'd have all the iron filings here or here, almost none in the middle. So I can see your little brains working and saying, hey, let's just cut that magnet in two, take the north pole over here, south pole over here, and we've isolated the poles, right? If you were to do that, if you chopped it right down the middle here and separated them, then suddenly this becomes the north, that becomes the south. You cannot ever isolate a monopole, a magnetic monopole, ever. If you do, you win the Nobel Prize, okay? Because no one's ever done it before. I don't think it's possible. Anytime you have a pole, you got the opposite pole. No matter how many times you break that up in pieces. If you think about your refrigerator magnets, they're about that big around and about that thick. One's a north, one's a south, okay? You can never separate the two. Okay, now, let's get to this picture. If you bring a north close to a south, look where all the field lines are in between the two, okay? Again, concentrated at the poles, you never have any filings here or here. Concentrated at the poles, but when you bring them together, they really are strong here and even strong here. It's like, and literally, they're pulling those together. You have to hold them apart. You cannot just let them there. If you did, they were going to come and collide. So you have to fix them that they're separated in order to do that experiment. Okay? But if you bring two norths close to each other, look at where the filings go here. Basically, never do they meet. The field lines never cross. They can connect like there, but they never cross. Now, these look like some of them are crossing, but they're really not. They're spreading out like this. And what does that indicate? Like poles repel each other. Unlike poles attract each other. A lot like our charges did. Like charges attract, unlike charges repel. Same thing with the poles. And it's all because of the field lines. And if you remember, most of electricity was all because of the field lines. Okay. Please look at your books. They skip so many things in this PowerPoint slide. Most of you are probably familiar with compasses. Those are little magnets, okay, that line up. What are they lining up with? What is a compass anyway? How does it do that? The earth itself acts like a magnet. And that's what this figure is showing. We'll get to it in a second. I was just going to show you. I wish they had these figures here. I guess I'll draw it for you. Here, I'll draw it on here. Okay? I'll go to red. That's what they did in the book. Okay? Again, let's ignore everything out here and everything over here. If this was indeed a bar magnet here, you know, one magnet, this north-south here, then your field lines, and here is the convention. They concentrate around the North Pole and the South Pole, and basically what they do, they flow north to south, north to south, north to south. Oh, they don't ever cross. Mine are not doing well. And they do it in both directions here, north to south, north to south, north to south. So you have a concentration of field lines there and there, almost nothing in the middle. And the convention is they always flow from the north to the south. Always flowing from north to south. Okay? Those are the field lines. Now the iron filings, you can't tell which way they're pointing, okay? But this is the convention. Here's how they do it. They would imagine taking a little compass and putting it down here, and the south-seeking pole of the compass is going to be attracted to the north, and the north pole is going to be repelled by the north and attracted by the south. So all along here, and this is what the picture in your book shows, figure 18.5, the B part there shows the compass needle pointing along the field lines. Always, if you put a whole string of compasses there, you would see that exact replication there. So in our modeling, we draw the field lines always pointing toward a south pole and away from the north pole. That's standard procedure. Okay? Question? Oh, okay. Okay. The figure 18.6 in the book is that figure right there. And by the way, this just shows it two-dimensionally. Remember, the field lines are three-dimensional. They go all over space. Okay. Now, we finally here get to this one. Why does a compass point toward the north anyway? Our globe, our Earth, acts like a big magnet. Okay? Now, we typically say the north is a north magnetic pole. Okay? But in reality, you got a problem there, don't you? If that's the north pole of a compass needle, it wouldn't point toward the north pole of the Earth, because they would repel each other. So in a reality, we should call this needle on the compass a north-seeking pole that's seeking the north pole. So actually, it would be like a south pole. But we usually call it north, so that makes the Earth's north magnetic pole actually the south pole, because all the compasses are pointing toward it. Okay, so it's a little bizarre, but it's true. Here's a problem, though, Houston. Now, they tilted the globe a little bit, and your actual north pole, the north geographic pole, the center of the Earth's spin is right here. The actual north magnetic pole is not quite right there. It's a few degrees off on one of the islands in the Bering Sea, or above the Bering Sea. It's in the Arctic Circle within that, but it's not on top of the North Pole. Now, why is that the case? I don't know. I'm not sure anyone's ever quite figured it out, but it's not there. I have a theory, but it's just a theory. I wouldn't even begin to bore you with that. But the reason they think the Earth is a magnet, we know it is. I mean, magnets point that way, okay? But the reason, and by the way, yeah, this is showing the same thing. The true geographic North Pole is here. The actual North Pole is off just a little bit. Now, actually, down here in the southern hemisphere, they're off worse than they are in the north. They don't show it, but the South Pole is in Antarctica, and the South Magnetic Pole is actually outside the Antarctic Circle. It's more than 23.5 degrees away. It's about 24 degrees off. This one's within, I'd say, 15 degrees. The north is. So they're not exactly opposite each other either. Okay? But what that means is a magnetic compass is going to point toward the magnetic North Pole, not the geographic North Pole. So if you're somewhere close to the magnetic North Pole, you could be pointing due south, and it will say that's north, okay? Because it's pointing away from. It's rather strange. Most of the time we're not up there. I've never been up there and don't ever want to go up there, okay? But anywhere you're on the globe, you have to take that into account. Usually it's not too bad. Here in Alabama, we're less than 2 degrees off. So when our compass points north, within 2 degrees, you're pointing to the north. If you get up in Maine and Seattle, it could be 15 degrees off, or even more, okay? Something off anyway. Not 2 degrees like we are here. We're just lucky we're almost in line. If you drew a line between the geographic North Pole and the magnetic North Pole and followed that along here, you see you go almost through Atlanta, Georgia. So Birmingham isn't far off from that. So that's why we're only a couple degrees off. But out here in Seattle, you're quite a ways off there. Your compass is pointing this way where true north is off, and this isn't showing. Compass is pointing this way, true north is that way, so you're several degrees off there. But don't worry about that. Most of the time it doesn't matter. Okay. So that's why the Earth has magnetic field lines. Now, if you want to know why that's true, here's the theory. Is the Earth a solid ball of rock? No. What do volcanoes tell us? Somewhere in that ball of rock, you got liquid rock, right? Otherwise, you wouldn't have magma or lava flowing out of them, would you? So the inner part of the Earth is actually liquid. Now, why is that? Because all the pressure from the crust of the earth and then the mantle of the earth is pressing there, and just like rubbing your hands together, you produce heat. When you have all that force and pressure pushing all the molecules together, it gets so hot it melts the rock, and you become magma. So when there are breaks and crevices, like where the plates come together and create problems, then you can have volcanic activity along those cracks. Okay? Well, if you have a solid shell spinning around and a liquid core that's sort of staying where it is, you have, and by the way, that solid thing is not a perfectly smooth sphere on the inside either. There's rocks and jaggedness and stuff like this, so you have friction there too. And whenever you have iron, which is most of the core, the mantle and the core is iron or nickel, a little bit of magnesium and stuff, but mostly iron, and you're knocking off electrons, electrons are moving around. And guess what? Anytime you have a moving charge, you set up a magnetic field. Every time you have a moving charge, you set up a magnetic field. So that's why the earth acts like a magnet. Okay? Now, I can't begin to tell you why this is true, but here's what seems to be true. And again, this is my theory. It seems like to me, and this is from cores they've taken on either side of the continental shelves, of the Atlantic Ocean. They've drilled down and they found that the Earth has reversed its magnetic field at least 22 times. And in between those times, it's been very weak. So it looks like to me that the magnetic field, for some reason in the Earth, is going through a precession and seems to be, right now I think we're getting further from the geographic North Pole and heading down here, and at some time it's going to be pointing down here. And then it continues and comes back up here. The thing is, the time lapse, the best they can figure between these reversals is something like 17,000 years or something like that. Well, we haven't been in existence that long. All of our combined lives as human beings, when we've had a magnet is pointed toward the north, because we're in the middle of that cycle. But they do indicate by the cores that, sure enough, it has changed. All right. Now, here's what I was just talking about. This is 18.2, magnetic effects of current, or on current. Okay? No, of current. I said it right the first time. Here's a few people that you might be interested in reading about. One is Hans Christian Ørsted. He was the first guy who realized there was a connection between electricity and magnetism. I think other people have suggested it. He actually proved it. Was the first to discover the connection between electricity and magnetism. Okay? A little bit further down, you'll see Andre Ampere. Does his name sound familiar? Yeah, that's where we get the unit for current. Okay? He was a mathematician and physicist born in France. His work became the basis of scientific electrodynamic theory following Ørsted's discovery. Now look at the years that Ampere lived. 1775 through 1836. What happened in 1775? Second? I couldn't quite hear what you said. My hearing is so bad.
She said World War.
Did you talk about a war? Is that what you said? It's the Revolutionary War. Actually, our Declaration of Independence was 1775. So he was born that year. Okay? From France, by the way. Within 10 or 15 years of the Revolutionary War, or maybe 25 years, what happened in France? They had the French Revolution. So he was growing up at the time when all that unrest was in France, but somehow managed to produce a lot of really great physics, even though France was falling apart at the time. Okay? If you go on the next page, you'll find another name, Nikola Tesla. Okay? Now, he was much later. This was about the time of the U.S. war between the states, the Civil War. Okay, that's when he was born. But he was not born here. He was born in Croatia, but moved to the U.S. after the war between the states. And he worked with some pretty famous scientist, engineer, electrical wizard. The wizard of, what was the name of that street? Can't remember the name of it now. Thomas Edison. And Tesla worked under him for a while, then they split, broke off, and Tesla did some pretty incredible things himself. Okay? So, let's go back to Hans Christian Ørsted. Here is what he realized. All right. Now, notice what this is representing here. A battery. What kind of current do batteries produce? Say again?
Is it volts?
Well, that's the unit we measure, and that's also the parameter. Well, what kind of current? We have two kinds of current. Anyone know what they are? I've been mentioning them a lot in the last two classes. The ones you plug into the wall is? Say again? Okay, that's electricity, but what kind of current? Alternating current. And the other is?
What's that over?
AC. What goes with AC? Alternating current. AC slash DC. You never heard of AC? Okay, so what's that? I can't hear. Okay. What does DC stand for? Direct current. What does a battery produce? Direct current, absolutely. Okay? Now, here's what we got. A battery producing direct current, that means the current is flowing, it depends on your deal here, but the current flows in one direction. Okay? Now, if you take a compass and it's pointing north, which is maybe that way, but then you connect the switch, and then you'll see the compass needle align itself with the current that's produced with that direct current. Now, does an alternating current produce a magnetic field? In reality, it does, but alternating current is doing this. Back and forth, back and forth, back and forth, back and forth. So the magnetic field would be so fast you can't tell, okay? Because it's 60 cycles a minute, at least, I mean a second. That's really, really fast. So, no, you're not going to be able to see a magnetic field around an AC line. But around the DC, off a battery, you can measure with a compass. You can see it deflecting because it induces. Anytime you have a moving charge, you induce a magnetic field. Every time. It's just when they're going back and forth so fast, the fields are changing so rapidly you can't measure them. Okay? So, the compass below the conductor with the switch open. With the switch closed, now, yeah, this is what it's saying. Okay? With the switch open, no current going through there, this is actually pointing to north. However, when you close the switch, it points this way. Now, that's not true north. That's the north direction of that. North is that way. And now it's pointing this way. And here's why. The field lines around your a wire with the current, direct current flowing this way, take your right thumb and point toward the direction of the current flow. Your fingers are going to wrap around and show the direction of the magnetic field. Okay? So you see flowing this way, the field lines are this way, so since the magnet is underneath, the compass is underneath that, it is a magnet by the way, underneath that the field lines are going to point north that way. because your fingers point in the direction of the field lines. Okay? Place it on top of the wire, open circuit, it's going to point to the north. Close the circuit, and now, again, the field lines are coming this way, but now the magnet's on top, and so they're pointing in this direction. So the north, the compass point aligns itself with the field line. So it goes in the opposite direction. Okay. Now, I'm trying my best to figure out what in the world. What they've done, they haven't labeled it right. No, okay. I got it now. This wire is connected to the plus pole of the battery, this to the minus pole. Same here. But here, this wire is connected to the negative pole, this one to the positive pole, so now the current's going this way, with the current flowing that way. When it's underneath, sure enough, it points this way. So it reverses the flow if you reverse the polarity. Okay? Open the circuit. Now you got them wired originally. Close the circuit. Now with the thing on top, the current's flowing this way, so the north point's here. But if you reverse the polarity and have the current flowing from here to there, so it's flowing in that direction, now on top, north is this way, so it's pointing that way again. So this is illustrating that it all depends on the direction of current flow and where your compass is relative to the magnet, because the lines of force go around the wire. Okay? And that, I think, is what, this is showing, is called the right-hand rule. If your current flow is up, point your right thumb in the direction of the current flow, your fingers point in, or your right hand point in the direction of the field lines. Everything depends on the field lines. Okay? Now, there is, and this is why they mention ampere. I need some space to write. That looks like the best place to do it. Here is called Ampere's law. And for the life of me, or Ampere's rule, or Ampere's law.
Look like the right hand rule.
What's that?
Look like the right hand rule.
Yeah, well, no, you don't. I haven't written it yet. Here is Ampere's law. Let me get my pen back to dark because I made it red just so we could I could draw the field lines the way they did in the book. Here's Ampere's law. B is the magnetic field strength. That's what B is. It's equal to a constant that's called the permittivity of free space. Okay? Now, they don't say that's what it's called. Oh, there it is. They call it permeability constant. I think it's permittivity constant, but about the same. Okay? And by the way, we'll talk about the value of it in a minute. Times your current divided by 2 pi and then capital R. What in the world is your capital R? It's the perpendicular distance from the center of the wire. Okay? So in other words, your field strength is greatest here, lesser the farther out you get, because it's a 1 over R relationship. The field strength is also depends on the current. The stronger the current, the stronger the field. The magnetic field lines are the things indicated by the green arrows there or there. And again, it shows right-hand rule. The direction is right-hand rule. The magnitude is by that formula, which they call Ampere's law. Okay? And I did not remember that was Ampere's law. I thought it was somebody else's. But anyway, B is the magnetic field. Mu naught, that symbol is called a mu. It's the Greek lowercase m, mu. I is the current, and R is the perpendicular distance from the center of the wire. So it falls off as a 1 over R relationship. And that mu naught itself is 4 pi times 10 to the minus 7. And the units for it are capital T. We haven't had that as a unit yet. M divided by A. Okay? Now, capital T, this is why Tesla was mentioned. They named the unit of magnetic field strength. The SI unit for magnetic field strength, Tesla. Okay? Now, long before that, it had been named the Gauss. That was magnetic field strength. But it was a SI unit. It was just a unit sort of like feet, you know. Okay? It didn't fit the SI plan, System International plan. So when they went to SI, they made the field strength Tesla. Okay? And this is sort of making sense. Because you see, if this has units Tesla meter per amp, this is in amps, so that would cancel out the amps here. 2 pi have no units. R is measured in meters. That would cancel out the meters, so that would be Tesla. B would be in Tesla. That's the unit for magnetic field strength. Okay? Now, they have another little thing here that I don't think you need to know, but I don't know this for a fact. Again, y'all are doing mostly sonograms, right? That's what you're training for. You don't think that's going to lead to something like magnetic resonance or MRI or any other technical thing like that? Okay. If it did, then you would be interested in magnetic flux density. So I'll just throw it in there because it's in the book. Here is another formula. It's a pretty simple one. B is equal to phi over A. Okay? Now, phi is magnetic flux, which we're not going to really do much with, but just so maybe you've seen it before. And A is not ampere. This is a parameter A. This is area. Okay? So don't confuse units with parameters. Okay, example 1. I think is only using Ampere's law, so don't believe we're going to be using this other one. So I'm going to actually take it off. They showed it in the text, but I thought just because they had it there, I would show it to you. Hopefully, we won't need it. A power line carrying 400 amps. You know what that power line is? Hot, okay? 400 amps is a huge amount of current. So this is your current, is 400 amps. And the third digit is significant. Is 9 meters above a transit used by a surveying student. So the distance of this is 9 meters above, so this is going to be your R, is 9.00 meters. Okay? That's pretty far, by the way. Just to give you an idea, I think I've done this before. I'm almost 2 meters high. Not quite close to it, because I'm almost a little over 6 feet. But a meter is a little bit more than 3 feet. So I'm 2 meters, and isn't there about another half of me up here?
Yeah.
Okay. So that would be 3 meters tall. The ceiling is approximately 3 meters. So 9 meters would be a 3-story building. This is only a 2-story building. Add another floor to it, that would be your 9 meters. So it's pretty far up there, okay? We're not talking about something real close here. But that's a lot of current, by the way, too, okay? So, it's above a transit used by a surveying student. And they say the figure is 1812, okay, B. There's your picture. If you go across there, it doesn't show, oh, there's the transit. I see it. Okay. Okay. So he's looking through that. Okay. I don't see what difference that makes, though. Find the magnetic field formed by the power line current above the transit. This is just a really made-up problem. let me make sure they don't have a figure of that. They don't, okay? You can look in your book and see the figure, okay? So you're looking for B, so that will be 4 pi times 10 to the negative 7 Tesla meters per amp times your current, which is 400 amps, which is ridiculously high, okay? So you see your amps go out, divided by 2 pi R, which is 2 pi times 9.00 meters, okay? Well, the good news here is the pi's go out, and 2 will go into 4 2 times, okay? And what that gives us here is 2 times 400 would be 800 times 10 to the negative 7th, and we're going to fix that in a minute, divided by 9. And by the way, the meters cancel out too, so I won't carry around the meter any longer. But this will be in Tesla. That's the only unit left. That's what we measure field strength in. So let's clean this up a little bit. This 8.00 times 10 to, if you move this decimal 2 places this way, making a smaller number, we make this bigger by 2 power of 2, so that would be 10 to the minus 5 over 9.00, and this will be in Tesla. So if you do 8, now y'all know how to enter scientific notation on your calculator? EE or EXP, that's the key you use. 8 EE or EXP, negative 5. That negative is not the subtraction key, it's the minus key in parentheses. Negative 5 divided by 9, and you'll get something on the order of 0.91 or 9.1 times 10 to the negative 6. Is that what you get? Okay. 9.19 times 10 to the minus 6 Tesla. Now that sounds pretty paltry, like a pretty small number, right? Nope, 8.89. Really? Okay, is that what you get? Okay, sorry. I guess it's 8.888, not 9.1. Okay. I was dividing by 11. Okay. Sorry about that. Y'all said yes, so I thought I had it right in my head. Okay. 8.89. Okay. You probably get 8.888888. Okay. 8.89 times 10 to the minus 6 Tesla. Okay. Ampere's rule shows that the direction of B, oh, we didn't give the direction of it. I don't think they told us the direction. It said power line carrying 9 meters above the transit. If the Earth's horizontal component of the magnetic field is, oh, that's the B part of the problem. Okay. Okay, sorry. Here's where they told us. If the current is moving from south to north, then Ampere's rule says, so south to north, your current is flowing that way, then the field line underneath it would be east to west. Okay. Now, B, I think that depends on I think that goes a little bit beyond what your probably your math background does. So we'll forget about that because y'all haven't necessarily had trig, have you? Okay. So don't worry about that. But what they're doing, they're talking about this figure here, and if this is the magnetic field line of the Earth, B sub E, and this is the field line caused by the power line, and I think they probably have these backwards in this one, then the angle between would be that angle theta, and you'd have to do the tangent of theta. So don't worry about that part. We won't even mess with the B part there. Okay. Now, a single wire carrying current produces a little bit of field. Not a lot of field. You have to carry an awful lot of current. And 400 amps is ridiculously high. Okay? But what happens if you get clever with it and take that current carrying wire and now wind it in a coil? Okay? Every one of these, now your right-hand rule tells you that the field lines are pointing that way inside the coil and this way outside the coil because of coiling it that way. So every time you do a coil, you increase the field almost by the number of turns. So therefore, we use those a lot. A coil of wire carrying a DC current is called a solenoid. And that's what this is showing here. Now there's some good pictures beforehand, and I wish they had shown it in here, but you see what I was just saying, if your current going this way, right-hand rule has the field lines coming around this way, so you just produce a little field there. But if you make a loop there, then all those field lines that are coming this way are doing this all the way around, which means the arrows are all pointing, let me see which way they did the loop. Yeah, all pointing out toward you, and all the, on the outside, they're pointing back behind you. So a loop is going to reinforce those. And then you make a series of loops, and you get a very strong magnetic field. Okay? And this is called, okay, so the magnetic field in a coil, the iron filings, that's iron filings there, show that the magnetic lines of force from the magnetic field coil of red wire, it doesn't have to be red, but they're just telling you that's a red wire, charged with electric current. What kind of current? Say again? What you say? I can't hear.
Awesome.
No, it has to be direct current. Has to be direct current for this to work, because alternating the field line will be going back and back and forth. You want it to be constant. So if you're, you see, the current is coming up this way and flowing this way. So yeah, your field is pointing north this way. So you form a very strong magnetic field right in the center of that thing. And it's strong here and strong there. North, south. Okay? Iron filings show this. You don't see the direction in it, but you see, basically you see your field lines. Just like they're showing here, your field lines are this way, and then they wrap around on the outside like that. Okay? That's called, let's see if they say it here. That's called the solenoid, by the way. Okay? And I don't know they're doing this. I can't. This is supposedly showing the little compass needles, but it's such a fuzzy picture I can't tell. In the book, it's probably a little bit better. Okay. Now, what you don't see in the picture in the book or here is your power supply up there, the battery. The DC power supply. Okay, I thought they were going to name it. I guess they don't. Yeah, they do in the text. A coil of tightly wrapped wire is called a solenoid. That's not all that tightly wrapped. That is a lot closer. The left side of the solenoid on this one acts like the South Pole. The right side acts like the North Pole. It just depends on which way you coil it and which way your current's flowing. Call it the other way, you flip them, or change the current, you flip them. Okay? So hold the solenoid in your right hand so your fingers circle in the same direction as the current. The direction of the thumb points is the northern orientation. So again, another right hand rule. So if you point this, you see here's your current flowing this way, and it's starting on the back side. So take your right hand, and wrap it around in the direction the current is flowing. There's your north pole, that's your south pole. Okay? That's what they're indicating here. But you have to know two things: which way the coils are wrapped and which way the current's flowing. Okay? And that determines your north and south poles. All right. Now, goodness gracious, they skipped so many things. Let me give you another formula they have here. For a long coil that is tightly turned or wrapped, the field strength at its center, so this is the field strength, the magnetic field strength, is that good old mu naught, remember 4 pi times 10 to the negative 7, all those units, I times N, where N is the number of turns in the solenoid. No, turns per unit length. Turns per unit length. Now the reason they say tightly wrapped, that means your R is very small. So you don't have to account for that here. Okay. Unfortunately, we're out of time, aren't we? Okay. Whoa. All right. Well, guess what? We're only doing in 18, 1, and 2. So when we finish our next example, example 2, then we jump all the way over. We may just talk a little about the other, but jump all the way over to 18.7, which is 1 paragraph, okay? 2 paragraphs, okay? And then we'll do 19, okay? Is that right? Yeah, 19. And 19, we just do 2, 3, I can't tell if it's 4 and 5 or not. It looked like I may have erased 4. We'll do what we can in 19, and that'll be it. So we're going to wrap up. I'm almost surprised at myself that we were able to finish all this. All the faults that the book has, it moves pretty quickly. Okay. I hope it's not too fast for you to understand. But let me give you the tests. I gave Camry hers, and all the rest of you are here, so that's good. This first test is a 17, chapter 17. And you should be able to do all of it right now. I mean, not right now. Before you leave, okay. This will be, this is stuff we've already covered, okay? All right. Now, the next test, and only because you asked for it, you got it, Toyota, okay?
We did not want it.
All right. Number 1, I think we've already done. Number 2, pretty sure we've already done. Number 3, we just hit upon it. Okay? That last thing I just put on the board, I think we'll do number 3 for you. Number 4, it should take care of that one as well. And the rest of them, 5 through 10, are going to come from chapter 19. So don't worry about those unless you just want to look ahead and work on them. So 1 through 4 you can probably do already. You ready for that? Okay. And see, he's already finished. No, I'm just kidding. That was the previous one.
So 5 through 10 is chapter 19.
That's one. No. What I said, don't get panicky that you haven't seen those last 6 questions on the second test, because that's what we're going to cover on Monday. But if you want to, you can go and finish the first test and turn it in Monday. Okay? So you can do the first 4 on the second test if you choose. And if you choose to do more, you can do that too, but that's completely up to you. I'm not requiring it of you. All right, any questions? Okay, it'll be so sad next week, won't it? Last day of class, oh, get over it. Okay. All right, good deal. This has been a fun class. Have a good weekend.